Hello students, now in this video let us see steps for solving linear homogeneous recurrence relation of order k. And later on, after taking steps, let's take the example on the same one. Steps for solving linear recurrence relation but of which kind? It is of homogeneous. Of order k. Let us see this. Now the first step is that we have to write the characteristic equation. Write the characteristic equation of given homogeneous recurrence relation. Now already we have seen that thing in previous video. How does that will be? Which is as it will be C0 alpha raised to k plus C1 alpha raised to k minus 1 plus C2 alpha raised to k minus 2 plus so on up to what? Ck, and that is equal to what? 0. It will be as such. Fine. Now after writing this, the second step says we have to find all roots of this characteristic equation. That are what? Characteristic roots. So find all roots of characteristic equation. Find all roots of characteristic equation. These roots are called the characteristic roots. Of this characteristic equation. Fine. Now the third step, depending on the nature of roots, as we say earlier, that nature of roots means what? That they may be same, they may be different. So in that one, first suppose the roots alpha 1, alpha 2, so on up to what? Alpha k. Suppose all are distinct, are real and distinct. Then if they are real and distinct, then the homogeneous solution of linear recurrence relation, linear homogeneous solution of linear homogeneous recurrence relation is, how does we will write it as? Alpha r, sorry, not alpha, it will be a. It will be what? AR, and here H we will write, as I say earlier, H for homogeneous. Now it is for real and distinct. It will be A1 alpha 1 raised to r plus a2 alpha 2 raised to r plus a3 alpha 3 raised to r plus so on ak alpha k raised to r. This is about the real and distinct case. Now, second case, if suppose two roots are repeated. Two roots are what? Repeated. Means what? Suppose two of them are what? Same. Say, let me say alpha 1 and alpha 2 are what? Same. So, let me write it as alpha 1 equal to what? Alpha 2. So, alpha 1 alpha 2 are same but other are different. Fine. So, they are equal. Then the homogeneous solution is. Then the homogeneous solution is. How does we write them? It will be ARH, that is equal to A1 plus A2 alpha. A1 plus A2. A1 plus A2, not alpha, sorry, here R. A1 plus A2 into R. Alpha 1 raised to R plus alpha A2, A3, alpha 3 raised to R. For alpha 1, alpha 2 we have written these two. These are actually two terms. Fine. Now next one, A4 alpha 4 raised to R and so on AK alpha k raised to R. Remember here we will take a linear factor A1 plus A2R, then alpha 1 raised to R for if it repeat twice. Now let me take in the same one. If three roots are same, sometimes it may happen three roots are what? Same or what? Repeated. Three roots are repeated. Say, suppose alpha 1 equal to alpha 2 equal to what? Alpha 3. Then the homogeneous solution is. Then the homogeneous solution is. How does we write in that case is this? It will be ARH, that is equal to A1 plus A2R plus A3R square into alpha 1 raised to R plus three roots are covered here plus A4 alpha 4 raised to R plus so on what? AK alpha k raised to R, and I can say and so on. Similarly, we can write for if 4 roots are repeated and so on. 5 roots are repeated. If all are repeated, then we will take such a increasing power factor over there. Fine. And the last step is that what will be the first step? Steps are very important here. We have to solve those linear recurrence relation. Here, the step first is what? We have to write the characteristic equation. Later on, we have to find out those roots of those characteristic equation. Now, the homogeneous solution is depend on the nature of roots. If roots are real and distinct, we will get that solution will be as such. If 2 roots are repeated, it will be as such. If 3 are repeated, it will be as such, and so on. Now, the last step says simply if k initial conditions are given to us to find these k unknowns in this homogeneous solution. Here A1, A2, A3, so on up to what? AK. Similarly here also K. So obviously K linear so constants we will get here, and simply we have to put up them here. K initial conditions are must given to us. So step 4. Let me write step 4. Then we will solve the example. Already I explained you step 4. So, what is step 4 here? If K initial conditions are given, we can obtain K linear equations with K unknowns. And while solving those equations, we will get the values of those unknowns. For your understanding, I am simply write these one in a bracket. Which are they? These are these one, A1, A2, so on up to what? AK. These one we have to find at last and substitute them in the homogeneous solution. Now, let us take the example so that you will get it. So, let me take first example. Solve the recurrence relation. Solve the recurrence relation. Now, suppose the relation will be given to us. AR minus 5U AR minus 1 is equal to 0 with A1 equal to what? 20. This is given to us. Now, what are the steps is? First of all, we have to write the characteristic equation. So, solution for this. Now, the given recurrence relation is what does that? AR minus 5U AR minus 1 is equal to what? 0. Therefore, the characteristic equation is what does the characteristic equation here? AR will be replaced by alpha and this AR minus 1. Last term we will skip here. So, alpha minus what? 5 is equal to 0. This will be the characteristic equation here. And that gives us alpha is equal to 5. So, here alpha equal to 5 is what? Is a characteristic root. Okay. Now, one more thing you can remember here. Here look at here. Here R minus 1th term is here, right? AR minus 1. So, this 1 will gives us the value of K. So, here I will get it is alpha raised to what? 1 minus obviously here alpha raised to 0. So, that will become 1. As such also you can remember it. Now, here this is a characteristic root. Therefore, the homogeneous solution is now it is only 1. So, no need to check about the distinct, real and all these. It is only one solution. Homogeneous solution is, here in this case, homogeneous solution is what? AR is equal to what? A 5 raised to what? R. Alpha will be 5. So, alpha raised to R. A will be a constant. That constant we will obtain using this initial condition. Now, we have A1 equal to 20. So, let us substitute here. Let me call it as R, star, sorry. Then R will become 1. So, A1 equal to 20. Therefore, this star implies, what does this give? This gives A1 equal to A 5 raised to what? 1. So, that will be A1 is 20. So, 20 is equal to what? 5A. So, that gives A is equal to how much? 4. A is equal to 4. Therefore, star becomes star will gives us what? AR is equal to what? 4 into 5 raised to r, and is the required solution. Is what is the required solution? Is the required solution here. Now let's take the next example. Next example, solve the recurrence relations Now suppose the first one is AR minus 1 minus 6 AR minus 2, that is equal to 0 with A0 is 5, A1 is 0. Second one, AR minus 6 AR minus 1 minus 9 AR minus 2 is equal to 0 with A0 is 1 and A1 is what? 6. This is given to us. So let me solve them one by one. So let me take solution of first one. Suppose now the given recurrence relation is what does that? It is AR minus 1 minus 6 AR minus 2 is equal to what? 0. Now as I say in previous example, here K will be what? 2. So the characteristic root we will write as alpha raised to 2. So therefore the characteristic equation is it will be alpha square minus alpha minus 6, that is equal to what? 0. While taking this as a K, we will skip this term. This term will become alpha raised to 0, that is 1. Now what are the roots of this? Here product should be minus 6, sum should be plus 1. So it will be 3 2s. So here I will get alpha plus 2 into alpha minus 3 are the factors of this. This is the quadratic equation. You know various ways to solve the quadratic equation. You can easily solve that or either factorize it as such. So that will gives me alpha is equal to what? Minus 2 and what? 3. So I can say here the characteristic roots are what? Minus 2 and 3 are distinct. Are what? Distinct and real. Are real and distinct. So we can use the case 1 here. Therefore the homogeneous solution is it will be AR H, that is what? A1 into minus 2 raised to R plus A2 into what? 3 raised to R. Now once we get this homogeneous solution, simply we have to use the initial conditions to find the values of A1 and A2. So now we have, let me call it as star. Okay, so we have A0 is equal to 5. A0 means R is equal to 0. So let us substitute here R is equal to 0 on both the sides. Our right hand side is already 5 given to us. So simply we will substitute it here. So for A0 equal to 5, star becomes, how does the star will gives us? It will be A1 into minus 2 raised to 0 plus A2 into 3 raised to 0. That is equal to what? 5. Fine. So that is what. Now you know anything raised to 0 is what? 1. So here we get a1 plus a2 is equal to what? 5. Now again a1 is equal to what? 0. So again star becomes, this is a1 into minus 2 raised to 1 plus a2 into what? 3 raised to 1. That is equal to 0. So it will be minus 2a1 plus 3a2 is equal to what? 0. So these two equations we will get here. As we have written in the steps that we get k linear equations in k unknowns. So here a1, a2 are our unknowns. We get two equations in these unknowns from initial conditions. Fine. So now solving this, while solving these one, so solving this we get, you know how to solve. These are linear equations, simultaneous linear equations. You have to solve either by elimination method, cross multiplication method, whatever you will use. So you can solve these. Solving these two equations, we get what does the values? We get a1 is equal to 3 and a2 is equal to what? 2. Hopes you know how to solve these. If you don't know, let me explain these one here. Look at here. Let me explain this. This is equation number 1, or let me write it here itself. This is equation 1. a1 plus a2 is equal to 5. Here minus 2a1 plus 3a2 is equal to 0. So let us multiply here by 2. So it will become 2a1 plus 2a2 is equal to what? 5. So and this will be as it is, minus 2a1 plus 3a2 is equal to what? 0. So now, sorry, not here 5, here it will become 10. Okay. Now look at here, why I have done it. This is minus 2. If I do here plus 2 and I will add them, a1 get cancelled. Simply a2 will remain. This is an elimination method. So simply we will add them. These are get cancelled. Here it will become 5a2 and this will be what? 10 plus 0 will be 10. So it will be 10. So that gives us a2 is equal to what? 10 upon 5. So a2 is 2. Once we get a2, put them in any one of these one. So this is easiest to put up here. So a2 will be 2. 2 will go to this right hand side. It will become negative. So 5 minus 2, that will be 3. So a1 will be 3. As such we can solve this. Fine. Now once we get the values of these constants, simply we have to put them in a star. That is our required solution. Hence the required solution is, what does that? It will be ARH, obviously it is homogeneous solution, that's why this one, equal to a1 is 3 into minus 2 raised to r plus a2 is our 2 into 3 raised to r. This is our required homogeneous solution for this given recurrence relation. This is first one here. Now let us solve the second one also in a similar manner. So for second one, simply let me do here B. Okay, the given recurrence relation is what? AR minus 6, AR minus 1, minus 9, AR minus 2. Here let me take here plus. It will be more useful again. That is equal to what? 0. So now again k is what? 2. So let's write the characteristic equation. Therefore the characteristic equation is what does that? That will be alpha square minus 6 alpha plus 9 is equal to what? 0. If you look it carefully, this is nothing but alpha minus 3 square is equal to what? 0. So that gives us alpha minus 3 into alpha minus 3. So alpha is equal to what? 3, 3. So 3, 3 will be the root of this equation. This is a characteristic equation. 3, 3 is the root of this one, and it repeat twice. Therefore, the alpha equal to 3, 3 are the repeated characteristic roots. Are the repeated characteristic roots. Therefore, the homogeneous solution is. Therefore, the homogeneous solution is. What does the homogeneous solution? ARH. Now it repeat twice. So ARH is equal to A1 plus A2R into what? 3 raised to R. Twice. 2 times. So already we have seen this in theory part. Let it be. This is what? Raised to R. Let it be star. So now star. Now let us see how to find these A1, A2 using initial conditions. So we have A0 is equal to what? A0 is 1. So that gives us A1 plus A2 into what? 0 into 3 raised to 0. That is equal to what? 1. So that gives, look at here, A2 into 0, so that will become 0. 3 raised to 0 will be 1. So A1 plus 0 will be A1 into 1 will be A1. So overall, while solving, we will get A1 equal to 1 from here. And A1 equal to 6. So that gives A1 plus A2 into 1 into what? 3 raised to 1. That is equal to 6. So we get A1 plus A2 into 3 equal to what? 6. That is A1 plus A2 is what? 2. Now substitute A1 here. We will get, now using A1 equal to 1, we get A2 is what? A2 is also 1. Okay. Therefore, the required solution is, here it will be ARH equal to 1 plus A1 1, A2 1. So 1 plus R into 3 raised to what? R. This is our required solution for this recurrence relation. As such, we can easily solve the homogeneous recurrence relation. Now, here we will stop. In next video, we will see some more examples on a same one. Thank you.